Uh, Today our topic is to understand the block diagram of a memoryless digital modulation scheme. Actually, we will see how the digitally modulated signals are represented, and then we will move towards the pulse amplitude modulation. Let's start with the block diagram, and first of all, we see how the if if we observe our system, usually in the target of a communication system or a digital communication system is to transmit the sequence of bits. Suppose you have some sequence of bits here at the transmitting end, 0, 0, 1, and so on. The transmitter would a transmitter is required to transmit this sequence of bits to the receiver successfully. Right? It transmitted over some medium. We call this medium as a channel. So this is our channel. So our signal passes through the channel, and the purpose of communication system is to the purpose of the transmitter. The purpose of the transmitter is to transmit it successfully to the receiver. So transmitter would like to transmit this sequence successfully to the receiver. Well, one of the basic tasks, one of the essential operations or tasks at the transmitter is modulation. One of the essential tasks is modulation, and because we have digital systems, digital processing at the transmitting and the receiving end, so we mainly discuss the digital modulation schemes. So moving towards the digital modulation schemes, I would like to draw the block diagram of my system. So if you observe a modulator at block level, suppose this is a modulator, and you have some input to this modulator, which is usually bits, because you have bits at the transmitting end, right? Some sequence of bits, and you give it to the modulator. These bits can be the data from your hard disk, binary sequence, and before transmission we want to represent these bits by some waveforms. So we can just transmit it one bit at a time, or we can group these bits into k. We can parse it into a group of k bits. So this is a group of k bits. So each k bit group is assigned to this modulator, and it gives you some signal as m of t for each k bit. And you are familiar, as we know, that if we have m number of unique symbols as m of t, and this m is of course 2 raised to the power k. If you have m number of unique symbols, it outputs these symbols, the modulator. So if we have m number of unique symbols, each symbol can carry k bits. You can just substitute this k, put the values of k equal to 1, 2, and so on, and you will get the values of m which are equal to 2, 4, 8, and so on. So if we group the bits in a group of k bits, we should have m unique signals to carry those k bits. Just for simplicity, let's give some value to these k bit group. suppose I give this a value, and let the value, suppose I have k equal to 3. I am grouping it into 3 bit. I am parsing the data or the binary sequence in group of 3 bits. So if 3 bits, it means I should have unique 2 raised to the power 3, 8 unique symbols. So 8 unique SM of t. 8 unique SM of t. We can say that M is from 0 to 7. So we should have S0 of t for transmission, S1 of t, and so on up to S7 of t. So these are the 8 unique bits, and each 8 unique symbols, and each symbol now is capable of carrying 3 bits, right? So suppose if this is for all zeros, 0, 0, 1 and 1, 1, 1. So we can group this our sequence, which may be some sequence like this, in group of 3 bits, and the modulator would assign some symbols to each group. For example, this one, if you have 3 bits here, just 3 bits, 111, so it would assign S7 of t for transmission. This way your transmission can be carried out using these symbols. So we have in a memoryless digital modulation scheme, the bits are assigned to the modulator, and modulator gives us SM of t for unique symbols. Now some SM of t which are unique symbols for these group of bits. Now we know that the data is in the form of bits. The binary sequence then is grouped into sequence of k bits, and each sequence is mapped to SM of t. So we can say that each sequence is mapped to SM of t, and as I mentioned that this M is from 1 to 2 raised to the power k. So the symbols, these are the unique symbols which are the output of the modulator, and we can have capital M possible signals, or we can say capital M unique signals and or symbols. Signals are usually transmitted over the TS symbol period. So this is our symbol period. TS is our symbol period. So these symbols are transmitted over TS. TS is also called signaling interval. So sometimes we call it signaling. This is our signaling interval or symbol period. So if we are interested in the symbol rate. If we are interested in the symbol rate and we represent it, suppose we are interested in the symbol rate, which will give us the data rate, of course. So the symbol rate, I represent the symbol rate by RS. So my symbol rate would be 1 over the symbol time. This will be the symbol rate, 1 over the symbol time. So this is the relation of our symbol rate in symbol with the symbol time. From here we can also say Now I hope it should be clear. If your symbol time, for example, if your symbol time is 1 millisecond or 1 microsecond, suppose your symbol time is 1 millisecond, so your rate, you can compute your rate, it means you are 1 millisecond, so you may be transmitting at a rate of 1 kilo 1 kilohertz or 1 kilo, because this is symbol rate, and 1 kilo symbols, actually you are transmitting 1 kilo symbols in 1 second. You are transmitting 1 kilo symbols in 1 second. So this is how we find our the relationship of the symbol rate to the signaling interval. Now as I mentioned that each symbol carries k bits, so we can also find the bit interval. So if we move to the to find out the bit interval from here, it can be expressed as we just represent our bit interval by t sub b. So if each symbol carries k bits, right? Each symbol carries k bit, and the symbol interval or signal interval is ts. So we can divide it by k to find out the bit interval. So this is our bit interval. This is our bit interval. Let me write it here. This is our bit interval. So our bit interval is related to the signaling interval. We have the rate related to the signaling interval and the bit interval related to the signaling interval. You can also write it in this form. You can just go to write it. Ts is equal to log 2 of m, right? So instead of k, you can also use the number of unique symbols, log 2 of m, which is also correct. This we just took it from here, 2 raised to the power k. So of course our k is log m to the base 2, right? So this is we can just replace k in this expression, and we get this one. So this is how we represent our bit interval. Now moving towards the sometimes we may be interested in the bit rate of our signal, because usually if you see, people are mostly people know the bit rate instead of the symbol rate, while in communication we may also use the symbol rate. So if you are interested in the bit rate, you can find it out, and if you observe your symbol rate, we know that our symbol rate is rs symbols per second, right? So if each symbol carries k bits, so your bit rate would be k times rs. So we can just represent it by simply r, and we can say this is our bit rate. So our bit rate is k times the r sub s, right? So each symbol carries k bits. So when you have for example, as in the previous example, we had 1 kilo symbols, right? So if each symbol carries 3 bits, so we would be transmitting 3 k bits per second, 3 kbps, right? 3 kbps, 3 kilobits per second. Now sometimes we are also interested, along with these bit interval, bit rate, the symbol rate, we are also interested in the average energy of our modulation scheme, the average energy for transmission. So if you are transmitting, suppose we represent the energy of our signal, suppose we represent the energy by this eta sub m. So if we represent the energy by eta sub m and we are interested in the average energy, what we can do, just sum the energy of all the signals, right, and divided by the total number of symbols. So if I have the E average is the average energy, so what I'll do, I'll sum all the energies of all these symbols. Suppose I have m unique symbols, right, m unique symbols. So sum of the energies of all these symbols divided by m. So this would give us the average symbol energy. This is the average symbol energy for any modulation scheme. You can have M-ary. We usually say that we have M-ary modulation scheme, and we can compute this average energy. Here we will see it shortly with the help of an example for the pulse amplitude modulation. Similarly, the average bit energy can be computed, and it is related to the average symbol energy. If you know this average symbol energy, you can just, if you know this average symbol energy, you can just divide it by k, because each symbol carries k bits. So average bit energy, which we will denote by B average, or sometimes only EB. So average bit energy can be computed from the average symbol energy, and you just divide it by k. Similarly, you can replace this k, you can replace it by log 2, right? So this is your average bit energy. We will see it shortly for our pulse amplitude modulation, that we actually compute our average symbol energy using this expression, and the bit energy can be computed from the symbol energy if you know that each symbol carries k number of bits. So sometimes we are interested in the average power. So if a communication system is transmitting an average energy of E average symbol energy, or this one, the bit energy EB average per bit, so it's transmitting, let me write it over here. So I'll move to the free space. If we have this average bit energy, or we say this is the energy per bit, and it takes t sub b seconds, right? T sub b seconds, just for the time taken by one bit to transmit this average energy. Then the average power which is sent by the transmitter, the average power which is sent by the transmitter can be written as the average bit energy over t, right? So the average power is the energy over the total energy, or the average energy. The average power is the average energy that is transmitted in TB seconds over the time interval, over the bit interval. So it's very, if you compare it with your previous knowledge, what actually you do, the definition of energy is the definition of, if you compare it with your previous knowledge, you already said that the definition, the energy of a signal, the energy of a signal is the square of its integral, right? It's the square, if you have a signal Sm square t dt, the square of its integral. So usually this is the broad definition. The limits is from minus infinity to plus infinity, but when we are talking about the signal which exists from 0 to t, so our limits change from 0 to capital T. This is the symbol duration. This is the energy of our signal. And if you see the power of your signal, this is from your undergrad courses. So if you see the power of your signal, what you actually do, you just divide it by time, and this E, right? This is from your bachelor course. The time, you can just say the average power is computed this way. So it's similar to this expression. We have the average bit energy and we have the time, the interval. So when we divide the energy by the time, we get the power. So the average power can be computed this way. Now moving to the pulse amplitude modulation, let's start with the pulse amplitude modulation. If I'll write it over here. So we have the pulse amplitude modulation. Pulse amplitude modulation. Pulse amplitude modulation, or sometimes it is written PAM, just abbreviation. So in pulse amplitude modulation, we have the same memoryless modulation. Keep in mind, we will have the same diagram. The input should be binary sequence or bits to the modulator, and the modulator output should be Sm of t. The generalized form of a pulse amplitude modulated signal is like this. We say our Sm of t is A sub m, and P of t for m, we have capital M unique signals, right? Capital M. And this AM actually it takes these values. To M minus 1 minus M, to M minus 1 minus M. So this is your AM, which is the amplitude. You can see that each in a pulse amplitude modulated signal, in the pulse amplitude modulated signal, each Sm of t differs from another one by this amplitude only, because the pulse P of t is same. And keep in mind, this pulse should not be, you should always keep this in mind, that the pulse is actually, this pulse is actually a symbol from 2 to t with a positive 1 amplitude. So this is your P of t. This one is your P of t. This is your P of t. Just to represent the P of t, now you can see that the P of t confined your signal to 0 to t only, because in the rest of the time it is 0. So whenever it is multiplied with some signal which extends from minus infinity to plus infinity, the resultant signal would be between 0 to t. So it is actually multiplied. Whenever it is multiplied with any signal, the result is a signal from 0 to t only, because in the rest it is 0. Rest of the time it is 0. So this is the representation of your pulse amplitude modulated signal. And the pulse can take these values, right? This m we already mentioned that m is from 1 to capital M. Now you can based on, let me explain this expression a little bit, so that you better understand the pulse amplitude modulated signal. Now suppose we have m equals 4, right? M equals 4. For M4, I would like to write my A1, A2, A3 and A4. It means I have 4 unique symbols. So what would be my A1? A1 be 2 times 1 minus 1 and minus 4. So if you see, your A1 is actually 2 minus 5, which is minus 3. And your A2 A2 is 2 minus 1 minus 4 and it is minus 1, right? Similarly, you can see that your A3 is minus 1 minus 4, so this is plus 1. And if you find A4 it would be plus 3. So these are the four amplitude levels. And you represent your signal in this form. Now if you go back to your if you write this one, suppose we write it in the we say that our Sm of t we say that our Sm of t is Am p of t. Actually this pulse we already know. This may be it's the simple pulse I have shown it to you, so we already know this pulse. So our signal S1 of t is actually A1 p of t, and we saw that this is minus 3, right? Minus 3 times p of t. This is our signal S1 of t, right? Similarly S2 of t, if you see S2 of t, it is minus p of t. S3 of t is plus p of t, and S4 of t is plus 3 p of t. Now it can be seen that it is actually a one-dimensional signal. It is actually a one-dimensional signaling scheme. You are familiar with the dimension because here I hope that you are well familiar with the Euclidean space, right? So if you have if you are having a one-dimensional signal, you can plot your one-dimensional signal in this form, right? So if I say this is my p of t, right, x is p of t, so you can have a 0 over here, the origin, and now you can identify the signal points. You have plus 1, plus 3, minus 1, minus 3, and if you write your signal, your first signal point is here, which is S1. Second signal point is S2, then S3 Euclidean space, right, and S4. Now this is how you represent these pulse amplitude modulated signal in Euclidean space. So now if we are interested in the energy of the signal Sm of t, we are always interested in the energies of the signal. So we can compute the energy of the signal, and the energy of the signal would be the square of its integral, right? The Sm square. This is the energy of the signal. So just substitute that value. We have minus infinity to plus infinity. Let me change the marker. And here I have am square p square of t dt, right? So this is the we have to integrate on this for energy of the signal. Now if I go ahead to find energy, it would be m square, and m square can be, you can bring it outside this one, some amplitude, and now this is, what is this? It's integral what does this integral represent? This is actually the energy of the pulse. So you have am square, it's am square and the energy of the pulse, which I can represent by eta sub p. So the energy of the mth signal, or energy of pulse amplitude modulated signal, can be computed from this expression. You need to know the energy of the pulse. If you know the energy of the pulse, and usually we keep it unity, so it's actually the square of these, the energy is actually the square of these amplitudes, because this is you will see that this is usually kept as to be unity normalized. So we can compute the energy of the signal. Similarly, the energy EP, as I just said, that E sub p is the energy of the pulse P of t. If we are interested in the average energy now, very important, if we are interested in the average energy of our signaling scheme, how we compute it, just to be consistent with your previous knowledge, you should know that the average energy is the sum of the energy of all the symbols divided by the total number of symbols, right? So if I want to find the energy of the average energy, so I would like to sum this EM from M1 to capital M, and I would like to divide it by capital M, right? So this is the sum of the energies. Now substitute these values and you will get the expression for the sum. Now if you write M1 to capital M, and you can substitute EM, which is A square AM square E pulse energy EP, and this can be written as EP over M summation M1 to capital M AM square. Now as we know, for the pulse amplitude modulation, we have the AM is given, right? This AM is already given, and it is either plus minus 1, plus minus 2, plus minus 3, or so on, right? So we can compute this sum. We can also write it, instead of writing plus minus 1, we can just say that EP over M 2 times AM square, right? 1 square plus 3 square and so on, and this is M minus 1 square, right? The last is M minus 1. You can just apply, you can just use this expression for M equal to capital 4, and you will see that the expression is exactly like this. You can just compare it with your previous knowledge. So let me move ahead, and we see this is our average energy, average pulse energy. Now this sum can be written in compact form. So we have actually we have 2 times EP over capital M, and we have this summation. This is the square, right? This square. We have this summation. So this summation, it is actually the sum of the sum of the squares of odd numbers, right? It's the sum of the squares of odd numbers, and if you see the sum of the squares of odd numbers, it actually becomes equal to this one, this one. And how you can compute it? You can compute this sum you can compute this sum. Just browse the internet and just try to find out the sum of the sum of the squares of odd numbers. From there you can verify that this sum is actually equal to this one. You can verify that your sum actually equals to this one. So with this you have to browse this, right, and give me the result, whether you can prove this or not. So it's an easy proof. Just go through that proof and let me know. Now we can write our sum. In this form. We can say that, okay, our sum is equal to 2 times EP over M multiplied by M times M square minus 1 over 6. So this is our sum, and this can be now it can be expressed as M square minus 1 times EP. Now you can just cancel it out. So this is the average energy. This is the average energy, the expression for the average energy of average symbol energy in M-ary PAM. This is the average symbol energy for M-ary PAM. Now very easy. If you want to find out the bit energy from here, so it should be very clear. To find out the bit energy, what you can do, you have, if you want to find the bit energy, average bit energy, which is average symbol energy divided by k number of bits. So you already know the average symbol energy, M square minus 1 times EP over 3 is the average symbol energy. So if you divide this one by k, right? K, or let me write, instead of k, let me write log of m to the base 2. So what do you get? You get the expression here, M square minus 1 times EP over 3 log m to the base 2. So this is the average bit energy for your M-ary PSK. So it should not be like that. It should come from here. This 3 is not included. So this is the expression for the average bit energy of M-ary PM signal. We will continue this in the next video. So let me stop over here, and we will move to the next video for continuation from this point, from this bit energy.